Okay, so let's look at another solution to the wave equation, the Coachee problem for the wave equation. So in this example here, I've taken the initial condition to be some function phi here that is supported only in this interval right here. So the support of a function is the set in which it's non-zero, roughly speaking. So anyways, the function is identically equal to 0 outside this little interval here. So we say it's supported right around here. So this is the, I guess this is the interval from -1 to 1. And so again, as time increases, so as you go in that direction, you see this wave, this initial deformation split into two waves, one of which travels to the left and the other which travels to the right. And outside this region, it's identically 0. So I drew a couple of, or plotted a couple of different viewpoints of this particular function. And I wanted to show in particular what you see when you look at it from above. And so what you see is there's these lines emanating out to the right here, and then also to the left. And outside these lines, so in this let me switch to a different color there. There. So in this region out here, and in this region out here, the wave has not reached that region yet. So by whatever time slice you're looking at, the wave speed c has not allowed the signal to propagate horizontally that far. By that point in time. And so this leads to the idea of the domain of influence. And so what we have, so here's a schematic for a function. So suppose that the initial condition is supported only in this region here, the interval from A to B. Then what happens is we've got the negative characteristic on the left, and so this is x plus ct equals a. That's this line right here, this thick line, and we have the positive characteristic on the right, so that's x minus ct is equal to b, so the curve coming out of b. And then this part inside is the region of influence. So it specifies the locations in space that at a given time t can have been influenced by the signal coming from this particular wave. And then you can actually back up the thing in the reverse direction. So suppose we pick some location x0, t0. You can say, what signals can reach this point, x0, by time t0? And the answer is anything that propagates with speed c from over here, x minus ct0, to over here, x0 plus ct0. And so this region in here is called the domain of dependence. So events that are happening at this point, x0, t0, are dependent on things that happened inside this cone. And so we see that the characteristic curves here, whoops, first off, they carry the signal forward in space-time. With speed c, and let me just emphasize this is finite. And let's say c and minus c, because they're going in opposite directions. And also, they help us define a coordinate system c equals x minus ct, tau equals x plus ct. And this transforms the initial wave equation utt minus c squared uxx equals 0 into the new and simple PDE uxc tau equals 0. Let me make that a capital U. And so the key point is that for hyperbolic PDEs, this always happens. So hyperbolic PDEs always have characteristic curves that play these roles. So back here I wrote finite speed. That was just because I wanted to highlight some difference with the heat equation. So for the heat equation, it turns out that for any positive time, uxt is going to be strictly positive. This is an unfortunate side effect of convolution with the Gaussian, convolution with the heat kernel. That means that according to the mathematical formalism, heat travels infinitely fast, faster even than the speed of light, which we know from physics is not allowed. So that's a slight flaw in the problem. Luckily, it's so close to 0 that it doesn't throw off the calculations too much. Anyway, the other thing that I just wanted to point out about these hyperbolic PDEs and this conversion of coordinate systems here is the familiar analogy with what we have from geometry. If we graph a hyperbola in the xy plane, so this is going to be x squared minus y squared equals 1, then by finding a new coordinate system, so instead of taking this horizontal and vertical line to be my coordinates, if I instead took these diagonal asymptotes to be my coordinates, and called them u and v, then the equation would become uv equals 1. And so if that if it's hard to see that that's uv equals 1, then let me just grab this thing and see if I can rotate it. And now you can see that this is the same as v equals 1 over u, standard like 1 over x type graph. And so the parallel then is complete between, on the one side, uxc tau equals 1, and then on the other side, u tau minus u xx equals 0. Oh, sorry. I guess that was 0. Sorry about that.